Welcome back, everyone. For today's deep dive, we're going to be talking about efficient LLM inference over long sequences.
Okay.
And the paper that we're looking at is called Star Attention, Efficient LLM Inference Over Long Sequences by Akaria, Gia, and Ginsberg from NVIDIA.
Ah, very cool.
Yeah. And
this is a problem that I think a lot of people are thinking about
yes,
as we're trying to scale these models up.
Yeah, if you want to analyze like a massive code repository, or you want to look at, really long documents, books and things like that.
Exactly.
So
summarizing books.
That's definitely a challenge because of the quadratic complexity of self-attention.
Of course.
And, we've seen things like flash attention, and ring attention, and distributed strategies. But Star Attention kind of takes a novel approach to this problem.
Yeah, I'm excited to dive into this because I think they do a really good job of recognizing that we need to reduce the computational complexity, but we also don't want to sacrifice any of the accuracy or expressiveness of these LLMs.
Yeah, we don't want to throw the baby out with the bathwater or anything.
Exactly, yeah. So it's finding that balance, right? It's a delicate dance between speed and precision.
Yes, and it seems like they've done that through what they're calling a two-phase block sparse approximation.
Cool.
So maybe before we jump into the specifics of that, can you just give us a high-level overview of what is the fundamental problem that Star Attention is trying to solve?
Yeah. So at its core, the issue lies in the self-attention mechanism itself.
Right.
So self-attention is incredibly powerful because it lets us capture these really nuanced relationships within a sequence of text. But the number of computations required actually grows quadratically with the length of that sequence.
Yeah, it explodes. It gets out of control.
It gets really big, really fast.
Yeah.
Essentially, for every single word or token in your sequence, you're having to compare it to every other token in that sequence.
Yeah.
So you can imagine as that sequence grows, if you're talking about the entirety of, War and Peace, the number of computations is just enormous.
Right.
And so that's where this idea of sparsity comes into play, right? So rather than attending to everything, what if we could be really clever and only attend to the most important parts? And that's kind of the fundamental idea behind a lot of these efficient attention mechanisms.
Makes sense.
But, Star Attention takes a very unique approach to this.
So how does it achieve this selective attention?
Yeah. So they have this really elegant two-phase approach, and the first phase is what they call context encoding.
Okay.
And really what it focuses on is processing this potentially very long input sequence in a distributed manner. So imagine you have your long sequence, right? And you divide that sequence into smaller, more manageable chunks or blocks. And then you distribute those blocks across different processing units.
Oh, okay. So instead of one processor looking at the whole sequence, you have multiple processors.
Right.
Each taking a small chunk.
It's like divide and conquer, right?
Yeah.
But there's a really cool twist to this.
Okay.
So they have this concept of an anchor block.
Anchor block.
Which is essentially you take the first block of your sequence and you prefix every single other block with a copy of that first block.
Interesting.
So every block, except for the first one, has this anchor block attached to it.
Okay. So what is the role of this anchor block then?
Yeah. So the anchor block is really crucial because it allows us to approximate these global attention patterns without actually having to pay the full computational cost of attending to the entire sequence, right?
Right.
So each block, while it's processing its own little chunk of information, still has this connection to the beginning of the sequence through the anchor block.
So it's like a common thread running through all of it.
It's like a shared reference point for all of the blocks, so they don't lose sight of that overall context.
So how does this actually reduce the complexity from quadratic to linear?
Right. So because we're focusing attention within each block and with this anchor block, the number of comparisons that we're making is now proportional to the size of the block and not to the length of the entire sequence.
I see.
So that effectively brings down the complexity from quadratic to linear.
Okay, that's really clever.
Yeah.
So now we've taken care of this context encoding, but we still have to generate tokens.
Right.
So what happens in phase 2?
Right. So phase 2 is all about query encoding and token generation. And here's how it works. You have your query, right?
Right.
Which is usually much shorter than your context.
Yeah.
And what you do is you replicate that query across all of your processing units.
Okay.
So now each unit has a copy of the query,
Right.
and it's a signed block of context.
Okay, what happens next?
So each unit then computes the attention scores between the query and its little chunk of context. But instead of sending all of that information back to some central location to aggregate it, they use this really clever distributed softmax algorithm.
Okay.
And what that does is it lets them compute these attention scores and aggregate them in a distributed manner.
Got it.
So we're still maintaining those efficiency gains, even in the token generation phase.
That makes sense.
Yeah.
So that's the theory behind star attention, but how does it actually perform in practice? Did they evaluate this on any benchmarks?
They did, yeah.
Okay.
So they used some established benchmarks like Ruler and Babylon, which are specifically designed to test how well LLMs do on long sequences.
Okay.
And they tested this across a bunch of different LLMs, including, Llama 3.1, both the 8 billion parameter version and the 70 billion parameter version, and even some models from gradient.ai.
Okay.
So they really tested this quite broadly.
And what were the results? Did it live up to the promise of efficiency without sacrificing accuracy?
The results were actually really impressive.
Okay.
So they saw significant speedups, up to 11 times faster inference, compared to the baseline.
Right, that's pretty...
While still maintaining, 95 to 100% of the original accuracy.
That's amazing.
And one really interesting thing they found is that this performance improvement was actually more pronounced with larger models.
Oh, interesting.
Which is exactly what we want as these models continue to grow.
Right.
Yeah.
That's really good.
So really promising results there.
Now, did they dive a little deeper into these results? Did they look at how it performed on different types of tasks within those benchmarks?
Yeah, they did.
Right.
And their analysis of the Ruler benchmark categories actually provides some really interesting insights.
Okay.
So for example, for tasks like single NIAH, which stands for needle in a haystack, where the goal is basically to find a specific piece of information within a large context. Star attention did exceptionally well.
Okay.
Almost identical to what you would get with full global attention.
So for tasks that are more like focused information retrieval?
Yeah.
Sounds like it's a home run.
It really shines in that setting.
What about tasks that require maybe a more holistic understanding of the context? Like question answering or, summarizing multiple documents.
Right. So for those types of tasks, which fall under kind of the multi-NIH and question answering categories in Ruler, Star Attention did show a slight dip in performance, but it still maintained a really high overall accuracy, in the range of 95 to 100%.
Still very good.
And I think the researchers attribute that to the inherent limitations of this block-sparse approach.
So there's a trade-off there. If you need to have a very nuanced understanding of the interplay between different parts.
Right, exactly. Context. There might be some cases where that blockwise processing isn't as effective as full global attention.
Okay, that makes sense.
So it highlights this important point, right? That star attention isn't a silver bullet. It's a tool that has specific strengths and weaknesses.
Of course.
And so understanding those nuances is really important for selecting the right approach for a given task.
For sure, for sure.
Now, I'm really curious about one particular category in Ruler called multi-hop tracing.
Okay.
These are basically tasks that require the model to kind of follow a chain of reasoning through the text, right?
Yeah. So, connecting the dots across different sentences and paragraphs.
It's a challenging aspect of language understanding, for sure.
It's a really hard problem,
So how did star attention do on those?
So this is where star attention faced some challenges.
Okay.
It struggled to maintain accuracy on these multi-hop tracing tasks.
Okay.
And the reason for that is basically this lack of communication between the blocks, right?
I see.
So because each block is kind of working in isolation, it can be difficult for the model to kind of follow these long, intricate reasoning paths.
So if you need to connect the dots across really widely separated parts of the text,
exactly.
Maybe not the ideal solution.
Not the best tool for the job.
Got it.
But on the flip side of that, they found that on aggregation tasks, things like summarizing or extracting key information. Star attention actually performs significantly better than traditional methods.
Oh, interesting.
So it seems that this blockwise processing
actually lends itself really well to this type of task.
So it excels where a local understanding of the text is sufficient,
right,
but struggles when you need this global interconnected reasoning.
Exactly.
Okay.
That makes sense.
Now, one of the most intriguing aspects of star attention to me is this anchor block, right? And they did this really cool ablation study to understand its role.
It's this common thread running through all of the blocks. Yeah. But I'm guessing it's more than just providing some global context.
Right.
What did they find in this ablation study?
Yeah, so they were really interested in understanding, what is the anchor block actually doing? And they tested two main hypotheses.
Okay.
The first hypothesis was that maybe the model is just learning to attend to the anchor block because of its position, right? It's always the first block.
It's always in the same place.
So to test that, they did some experiments where they varied the position IDs of the anchor block while keeping the content the same.
Yeah.
And they found that it had very minimal impact on accuracy.
So the model wasn't just picking up on positional cues.
Right. It wasn't just about the position.
It was something more than that.
Exactly.
So what was the second hypothesis?
So the second hypothesis was that it's actually the content of the anchor block that matters.
Okay.
So to test that, they did a bunch of experiments where they replaced the actual content of the anchor block with different things.
Okay.
Like sometimes they just used a repeated token. Sometimes they used random tokens.
Okay.
They even tried shuffling the original content.
Interesting.
So basically, they were trying to disrupt the meaning of the anchor block while keeping the position the same.
So keep the position, screw up the meaning.
Exactly.
What happened?
And what they found was really striking.
Okay.
Whenever they messed with the content of the anchor block, the performance dropped significantly.
Oh, so that really suggests that the model is actually relying on the information that's contained in that anchor block.
So it's not just a common reference point,
right?
A meaningful common reference point.
Exactly.
That's letting the model make sense of the whole sequence, even though it's only seeing these little chunks.
Exactly.
Really cool.
It's not just a placeholder. It's really playing an active role in shaping the model's understanding.
Very, very interesting.
Now, the authors, they've done this amazing work demonstrating the effectiveness of star attention.
Yeah.
But they also acknowledge that, there are still some open questions and some areas for future research. Yeah.
Like what? What are some of the most exciting directions that you see this work opening up?
Yeah, I think one of the most immediate areas for future work is to kind of dig deeper into this anchor block. We know the content matters, but how do we determine the optimal content? Right. What are the best strategies for constructing this anchor block?
Yeah. Right now, it seems like they're just taking the first block.
Right.
But maybe there's a more intelligent way to do that.
Exactly.
Yeah.
So I think that's a really interesting direction. Maybe we can use things like topic modeling or even reinforcement learning to identify the most representative or influential segments of the input to use as the anchor.
That's a really cool idea.
Yeah.
And thinking more broadly, what about those tasks where star attention struggled a bit?
Right.
Like the multi-hop tracing.
Yeah.
Are there ways to adapt the method to handle those long-range dependencies and those complex reasoning paths more effectively?
Yeah, I think there are definitely some promising directions there. One idea is to incorporate some kind of mechanism for inter-block communication.
Okay.
Right? So instead of each block being completely isolated, maybe we allow them to exchange some information, either directly
or maybe through some kind of hierarchical structure.
Yeah, it's like adding bridges between those islands.
Yeah, like building bridges between those islands of information.
So the model can really traverse the entire text more effectively.
Exactly, yeah.
Cool.
And then on a more practical level, I think the authors also point out that we need to explore how star attention plays with other optimization techniques.
Right. We've talked about flash attention and KV cache compression.
Right, exactly.
But there's all these other things like low rank approximations, quantization, hardware-specific optimizations.
Right, the whole toolbox.
Yeah, maybe combining those with star attention could lead to even greater efficiency gains.
Absolutely.
Yeah.
I think it's really about finding the right combination of tools for your particular task and your computational environment.
For sure.
Right.
Now, I want to step back from the technical details for a second and think about the bigger picture.
What does star attention tell us about the future of LLMs?
That's a great question.
Yeah.
I think, to me, star attention signals a really important shift in our thinking as we move towards these ever larger LLMs with hundreds of billions.
Trillions of parameters.
Even trillions of parameters.
Yeah.
Efficient inference is no longer just a nice to have.
Right.
It's a necessity.
We can't just throw more compute at the problem.
We can't just brute force it anymore.
Yeah.
We need these smarter, more efficient algorithms.
Like star attention.
Like star attention, exactly.
Yeah.
And I think it's not even just about efficiency for efficiency's sake. It's about democratizing access to these powerful models.
Like that.
If we can make LLM inference faster and less resource intensive, we can open up so many possibilities.
It could be an everyday tool.
Exactly. Yeah, researchers, developers.
Not just these big companies with tons of resources.
Exactly.
Yeah.
And I think that's a really exciting future. And I think, star attention is a big step towards realizing that future.
So as we wrap up this deep dive, what's the one key takeaway you want our listeners to leave with?
I think the key takeaway is that star attention is more than just a clever algorithm. It's a glimpse into the future of LLM inference.
Yeah.
It's a reminder that we need to be ambitious in our pursuit of powerful AI, but we also need to be pragmatic.
We need to think big, but also think efficiently.
Exactly. We need to think big, but think efficiently.
Well said. Well said.
Yeah.
Well, it's been a pleasure exploring this research with you.
Likewise, always a great conversation.
And to our listeners, thank you for joining us on this deep dive into star attention. We hope you found it insightful, and we'll see you next time.